Okay, I'll share my screen and then I'll tell you about the assignments you have to submit. Okay, so this is the your assignment schedule which you have to submit. I have divided the assignment set in 9 groups. Uh, Set 1 having problem numbers. So these are problem numbers. Uh, 1, 10, 19, 28, 37. AP series, right? AP series with common difference 9. So similarly, set 2 starting with 2 with common difference. There are 54 problems, so each group will have 6 problems. So set 1, set 2, set 3. So everybody has understood this. Now, who has to do which set? Your roll number having a last digit 1, that means if some PHY, roll number means PHY. PHY 1001 or PHY 011 or 021, etc. The last digit is 1, that means they have to do the set 1. Last digit is 2, then you have to do the set 2. Okay, so 9 set, but there will be in the last case, last digit is 9 or 0. Last digit is 9 or 0, they will do set 9. You have to submit the hard copy of your assignment by 27/11/21. This date is the deadline for submission of your assignment by 5 p.m. I'll be there in my office, or I'll arrange to collect. Okay, and those who cannot, which are out of campus, please write to me, or cannot submit with proper reason why you are not doing practical classes, so that so if there are some proper logic, then I'll accept online copies of your assignment. Okay, so any question on this? Is that clear? Those who are present, anybody has any doubt, please ask. I have divided the problem set is circulated on long ago, I think in October or sometimes. It has 54 problems altogether. So I have divided into 9 groups, and it is very easy to remember that group 1 is starting from problem 1 and with the AP series in the problem numbers with common difference 9. So 9, so 1, then 9 adding 9, 10, adding 9, 19, etc. 2, then adding 9, 11, and so on. So up to 46. So 6 questions, 6 questions, 6 questions. So there is problem 1 to 8. Now, again, I am using very easy notation such that you can understand your question. If your roll number is PHY 123, if somebody's roll number is 123, then he or she has to attain the submit the problem set 3, because last digit is 3. Okay. Similarly, those who having roll number last digit 9 or 0, this is the only difference. Last digit is 9 or 0 is problem 9, because 0 set is not there. Set 0 is not there. So only thing I request you to write down your problems, exact problem on the assignment sheet itself, your roll number and problems number, actual problem you have to write in your assignment and submit hard copy by 20 next week. 1 week time is good enough. Okay, so let us go to the topic we were teaching, the central force. Toward the central force problem. So last time we discussed that uh, that if you have two body, m1 whose position vector is r1 and another particle is mass m2, position vector is r2, then Lagrangian we wrote was half m1 r1 dot square plus half m2 R2 dot square, and then there will be some potential depending on R1 and R2. So there is no velocity dependence, say. Okay. So this is the Lagrangian, supposed to be Lagrangian. But if it is for arbitrary potential, if this is arbitrary, then this kind of problem is extremely difficult to solve, because it has 6 bodies and then a non-trivial interaction. But if this potential is of central force type, then or central potential, then that means it does not depend on the angular part. So if the potential depends only on the separation between these two position vectors, only the function of R2 minus R1, then this problem can be solved by reducing it to a single body problem. So that we are going to discuss. We can go to the center of mass of this problem, and then we'll see what will happen. So suppose you have, this is the position vector of the particle 1, and suppose this is your position vector of particle 2. So this is a M2, this is your M1. So you can join this line, and somewhere in this joining line you have the center of mass. So let us call the center of mass position vector is R. Okay. So this is sorry. So this is your R2, this is your R1, and this is your R position vector. So you immediately you can express your capital R in terms of R1, R2, that definition of center of mass. So R is M1 R1 plus M2 R2 plus M1 plus M2. So this is by definition of position center of mass coordinate, and also radial coordinate I said R. So this radial coordinate I define R2 minus R1. So you solve this and substitute back in your Lagrangian. So what you'll get, if you solve, then you will find okay, so I'll not do this solution, you do this solution yourself and solve these two in favor of R1 and R2. For example, R1 you will get R plus M1 plus M1 plus M2 R. Similarly, R2 will get R minus no, I think first one will be minus. You can see because of R2 minus R1. This will be plus M2 M1 plus M2 of R. So now you substitute this R1 R2 in this Lagrangian. So if you substitute in this Lagrangian, then you will get a Lagrangian. Let me do this simplification yourself. So Lagrangian you will get half M1 plus M2 R dot square R vector dot square plus you will get half M1 M2 by M. This simplification you please do yourself. Do R vector dot square, and then potential was only function of UR. So I have 6 degrees of freedom. Remember, first particle is 3, second particle is this 3 degrees of freedom. So now that 6 degrees of freedom is now reduced to this Lagrangian, where center of mass has 3 degrees of freedom, R related to R, small capital R, and the reduce, this R is called reduced coordinate or relative coordinates. Let us say relative degrees of freedom is 3. Okay. But interesting thing by this mathematics we obtain is that, this potential does not depend on capital R, because of our choice that potential depends is R2 minus R1. So if it depends only on the relative coordinates, then so this is a free particle. So center of mass motion is free, no potential, no force. It is freely moving. You can see it is half mv square. So if you have half mv square, that for a free particle. So nothing else, nothing capital R is appearing. So center of mass is a free move. It moves in a straight line and with a constant velocity, right? So that is not interesting. So this is a free particle motion. So this system, if you consider, so this system center of mass is located here and it is moving freely in a direction. But we are only interested in the motion of particle 1 and particle 2 through the relative coordinates. Okay. So if we ignore the center of mass motion, because it is a free motion, so you are ignore means we are not considering. How you can do the ignore, how you can ignore, just take your coordinate system here. So instead of choosing your coordinate system at 0 0 here, you just choose at the center of mass your coordinate system. Okay. Now you are moving freely or you are at rest, doesn't matter, right? So both are inertial frame. Okay. So you ignore this key by choosing, let me write by choosing center of mass as the origin, or by choosing origin on the center of mass, by choosing the origin at center of mass. Okay, you can, so you are moving and then you are looking at the motion of the particle 1 and particle 2 through the relative coordinate. Okay, so this Lagrangian effectively reduced to a effective Lagrangian which has half m1 m2 plus m1 plus m2 r dot square r vector dot square plus ur. Okay, minus ur. So this I can write half mu r dot square ur. So this is a single particle or one body effective Lagrangian. So this by this procedure we know how you can reduce two body problem to single body problem. But this one body is not the either of the body m1 or m2. The mu is the reduced mass. Mu is m1 plus m 1 over mu is m1 plus m2 by m1 m2. That means 1 over mu is 1 over m1 plus 1 over m2. So this mu is called the reduced mass. So single particle, but that particle is single particle mass is the mu is the reduced mass. Okay. So it is the reduced mass of the system and particle moves with the reduced mass, and it is a single particle system. Okay. Okay. But immediately we get some information about this system. This is of course reduced mass and it depends only on the magnitude. So this system half mu r vector dot square minus ur does not depend on angular variable. This is basically mod R. You can think of in the beginning itself, we can tell the potential is scalar function, so it should be function of that depends on the magnitude of this position. Okay. Okay, so this does not depend on the angular variable. So there will be some coordinate angular variables does not depend. So that angular coordinate, suppose theta, and the momentum conjugate to angular variable will be conserved. This we know from our properties of Lagrangian. If some variable is absent, some coordinate is absent, then we have the corresponding momentum is. In this case, angular coordinate corresponding momentum is the angular momentum. So, angular momentum of this system is conserved. That means if you write m as the angular momentum, which is r cross p, this m is conserved. So, if this is conserved, that means dm, you can write dm dt will be 0, equal to, you can write r dot cross p plus r cross p dot. Okay. But this term is 0. Second term is 0 because p dot is nothing but the force, and force acts along this line. So, direction of force and direction of r, they are parallel, they are same line. Okay, so angle between them will be 0. So, it will be this and this direction is same. So, cross product will be 0. So, this implies that your p vector or r dot vectors, that means r vector, is perpendicular to the angular momentum, or your motion is taking place in a plane, say r and p, and angular momentum is perpendicular to that plane. So, central force motion, so we conclude that central force motion always takes on a plane. So, whatever motion I have, if I have considered central force, because I have assumed the potential depends only on the magnitude of R2 minus R1, and that force motion we can see from our these simple arguments that it takes in a plane. So, let us then we can simplify our Lagrangian. Our Lagrangian is half mu r dot square, or let me write r vector dot square times ur. Okay. So, this Lagrangian, let us say r, it is then a plane. So, I can write can describe by two coordinates. So, let me write in polar coordinate. So, x equal to r cos theta and y equal to r sin theta. So, cos theta, y equal to r, with this is a magnitude sin theta, right. So, r going to 0 to infinity and theta going to 0 to 2 pi will cover the whole two dimensional plane, right. R here r equal to root over x magnitude, so x square plus y square. Okay, so from here you calculate your so this your Lagrangian is half mu r dot square means x dot square plus y dot square times you so let me write it still r, because I'm going to write as the r and theta. So if you find your x dot y dot, calculate your x dot, calculate your y dot, which will be x dot will be r dot cos theta minus r sin theta theta dot, right. Similarly, y dot will be r dot sin theta plus r cos theta theta dot. So, you substitute, and if you substitute, you will get this Lagrangian half mu r dot square plus half mu r square theta dot square, then u r. So, the effective one body Lagrangian is now reduced in polar coordinate in terms of r theta with this Lagrangian. Okay, mu is the reduced mass of the system we have started with. Okay, it's clear. So now you can again see that theta is cyclic. that now it is very apparent theta is cyclic. There is no theta occurring in the potential, or nowhere there is theta, but there is theta dot. So del L del theta dot, which is nothing but the angular momentum m, should be conserved. So let us calculate that m equal to del L del theta. So del L del theta dot will be half mu r square, then 2 theta dot, right? So mu r square theta dot is the angular momentum. Angular momentum, and this is a conserved quantity. So let us denote by this the value of the angular momentum is L. So generally people small l, so r theta dot is like this is a constant quantity. So theta dot should be L by mu r square. Okay, so this will be using. So we have to solve for r and theta, but we already find that theta dot, this equation is simpler. So what will be the r equation? So this is also theta equation. You can find the theta equation will be like same thing will be. So this is your theta equation. So similarly you will get your r equation. Okay. So if you calculate your r equation, so what will be that? ddt of del L del r dot minus del L del r equal to 0, right? So ddt of del L del r, so it will be mu so mu r double dot first term, and there is no r dot here, then del L del mu. So minus, so if you differentiate r square term, then it will be mu r theta dot square mu r. So mu r theta dot square. Okay, then minus plus del u del r equal to 0. Which you can write in this form mu r double dot. Now theta dot we have already calculated, so in terms of constant, so mu r L square mu r square whole square. This I substitute theta dot from here equal to this, I take that side, so it will be your Fr. Right side it will be minus del u del r, which is nothing but your the force, central force. So this theta equation mu r double dot is this mu r, this will cancel, so L square mu r cube, right? L square mu, 1 mu will cancel, r to the power 4, r will cancel, mu r cube equal to Fr. So this will be your theta equation and r equation, and that was your theta equation. So if you can solve this, then you know this one body problem. But before solving, we'll get some interesting result in this system. First thing is that we saw that mu r square theta is constant, right? Is constant. That means you can write is that ddt of mu r square theta dot is 0. That means ddt of, I can write half r square theta dot equal to 0. I divide both side by 2 mu. 2 mu divide, so this mu get cancelled this side. So I dividing both side by 2 mu, you can get this. So what is this result that I am going to tell you? This is nothing but this half r square theta dot is nothing but your the area that if a particle moves in a curve, with the position vector r, then this is nothing but the area, and this equation says that aerial velocity is rate of change of area, aerial velocity dA dt, just a minute. No, this quantity is this half r theta dot is basically dA dt, aerial velocity, not area, aerial velocity. So this equation then means that so let us aerial velocity. So it's actually ddt of that equal to 0. So aerial velocity is conserved. So, but how this is aerial velocity, I'll explain. How this I'll explain. But aerial velocity is conserved. That you already know for Kepler's problem, that aerial velocity is conserved, that it will cover equal area in equal time. So that means if you have a motion, elliptical motion, then this see here, if you cover in 1 second, so this will be the area. But when you cover here, you will have a bigger, because this is length is large, this is small, but in 1 second it will cover the equal area. So area here and area here will be the same. So that is the aerial velocity is conserved, and that is true for Kepler's problem you have seen. Now I am saying that is true for any central force problem. Any central force problem, the aerial velocity. But I have to explain how this is the aerial velocity, that I am going to explain. Okay. So suppose you have this. Now a particle moves like a curve like this. Okay. Particle moves. So let us draw some position vector. So this suppose this is r, this is r plus dr, say, and say this is small, this is small time interval, so this angle is d theta. So when it is small, this you can make a perpendicular, and this area will be neglected, because I have drawn a bigger picture. But if you have a path, and if it is a very close, then any curve will be approximate by a straight line, right? So this area basically effectively for infinitesimally close, this will be the area under the curve. There will be very less or on infinitesimal, then this will be negligible. So this angle is d theta, so this line will be r d theta. So area of this triangle will be half, this is r d theta, this is r, so r into r d theta. But for this is infinitesimal, so this we can write change in area dA. So dA dt will be half r square theta dot. Okay, so this is the aerial velocity. Is that clear? So two important result we get. One is that aerial velocity is conserved not only for Kepler's problem, but any central force problem. This is a very interesting result. And other thing is angular momentum conserved, and the motion should be, whenever you have angular momentum is conserved, the motion should be on a plane. So two important things, two equation motion, effective one body Lagrangian we found. So many things we have learned. Okay, so the differential equation we get two variables, so two second order differential equation. So if you want to solve, there will be four unknown constants of integration, right? If you have a second order differential equation, the solution is always written in terms of uh, two unknown constants, right? So that, but then how to find these four constant is that actually the solution. So already we know that angular momentum is conserved. Angular momentum is conserved, and that is written m, not m. I should not write m. It is mu actually. Yeah. So mu angular momentum. Sorry, mu r square theta dot equal to L is constant. So from here you can find your theta dot is L by m r square. So theta will be theta 0 plus integration L m r square dt, right? So this is called the first integral, or first integral. Okay, so there are four integrals we need because four unknown constants. So this is first integral. Now second thing is the coming from the conservation of total energy. This is a conservative system, so total energy will be conserved. So total energy, how we'll write total energy, that is now I'll show you. So total energy, okay, so how to get that, let me tell you. So let us start from the r equation. R equation which we got, mu r double dot was minus uh, just a moment. Okay, minus L square m r q, and this time was minus del u del r. So I want in this form. I wrote fr, but this. So mu. I'm sorry. Why I'm writing m? This is mu. This is mu. This m is mu. This is also mu. Yeah. I'm. Let me see if there is no small m anywhere. So all are mu. See, in some book they just write in, but okay. So mu r double dot, and this also I can write in terms of, so if I write ddr of L square 2m r square, so what will happen? That's equal to 1 over r square derivative. So minus 2 L square 2m r cube. So 2 get cancelled. So minus L square mu, so mu again mu. So minus mu r square, this I can write is the derivative of L square 2 mu r square. So okay, so this is fine. Okay, so so this we can write. So this side it is minus, so I can write plus ddr of L square to mu r square is minus del u del r. Fine, because if I differentiate, it will get this term. So mu, so mu r double dot equal to minus ddr of u plus L square to mu r square. Fine, I bring everything this. So this also can be written as half ddr of mu r dot square, right? So when I take a r dot square, no. Uh, no. This we need little bit technique. Okay. So now I multiply both side by r dot, mu r double dot, then r dot, and this side also ddr of u plus l square 2 mu r square r dot. Okay. So then what I can write, this side I can write ddt of half mu r dot square. Let me check. So if I make a derivative of r dot, then it will be 2 r dot, then r double dot, and the 2 will cancel with this half. So it is like, you will get this. This side r dot and del r is basically minus ddt. ddr r dot is basically ddt, right? dr dt, so r dr will cancel dt of u plus l square to mu r square. So now I can write everything ddt half mu r dot square plus l square to mu r square plus u is 0. This is nothing but the total energy. Okay. This is total energy of the system. So this total energy of the system is also conserved. So I can write that half mu r dot square plus l square 2 mu r square plus u equal to E. This is total energy. So from here I can integrate r. So r dot square will be 2 by mu, and then r dot square, let me remove the square, square root. Then we have E minus L square 2 mu r square, right? No, what E minus U, E minus, sorry, E minus U. So I have written wrongly. So this will be E minus U minus L. And this, so r dot you can write, then r will be some r0, or you can write 0 to r0, this integration 2 by mu E minus U minus L square 2 mu r square dr dt. Or you can write r0 plus this. So this is the, these two integration coming from the conservation, they are known as the first integral of motion. Okay. So 4 unknowns, so you have already have to decision, and then other 2 you have to find, and how you will find that we'll discuss. So this equation, this solution, this also has a better way of writing solution. Let me write. This is dr dt. So you can write integration dt. This is dr dt. So integration dt is basically, you can write dr by root over 2 by mu E minus U minus L square 2 mu r square. Right. So this is basically known as first integral motion. Sometimes we ask what is the first integral of motion. So it should be, suppose your motion is between r0 to r. So this will be the, so t equal to r0 to r dr root over 2 by mu E minus U L square by 2m r square. So these are the integral of motion. So now we'll find the solution Okay, so 4 constant you need, 4 constant we have now. L E is a constant, L is a constant, and R0 will be another constant of integration, and then L0. I wrote somewhere L0. Let me see, theta 0, theta 0. Yeah. So this, so I said that there will be 4 integration of constant. These are the 4 integration of constant. Okay, good. So far, so good. Do you have any question? So I am here 45 minutes. So let me go ahead. If you have any question, please tell me. This is your third last class. Next week, oh, I don't know. Next week probably I need 2 classes. So I'll talk to Krista, and I don't know whether he will take additional class or. Uh, okay. So no question, as everything is simple, it seems to you. Okay, very good. So now E, as I, let me change my color. E I wrote is half mu r dot square kinetic energy. Then there is a potential energy, and there is also some additional term coming from our analysis, which is L square to mu r square. Okay, where L is the magnitude of the angular momentum. L is the magnitude of angular momentum. Okay, good. So this also I can write this as, this is also a potential energy, because this is a function of r. So I can write half mu r dot square. This r is not a vector; it's the magnitude of that r. So it's a single variable. When I write a vector, it may be in 2 dimensions, 2 variables, but it is only a single variable. So mu r dot square plus, now these 2 quantity I define together and write a effective potential. So this is the effective potential. So your effective effective potential is the original U potential appear in the Lagrangian plus L square 2 mu r square. So this is effective. Now I am going to show you that looking at this effective potential, we can predict the motion of the particle, what kind of motion the particle will have. And for that we'll consider some specific example of, and specific example means U has to be some specific form. Okay, so this will help to predict the uh, overall uh, motion or trajectory of the particle. This is very important. So let us consider U equal to the Kepler's problem first. So U equal to minus alpha by r. Okay, alpha greater than 0. Okay, so your U effective then will be minus alpha by r plus L square 2 mu r square. So what will be the first thing, you have to look at the graph, how this will be the graph. So tentative, you have some idea. Suppose if I want to draw, what will be the graph of U effective versus, so you have to draw the graph U effective versus R. Okay, so let me first what will be the graphs looks like. It is 1 over R square. So 1 over R square graph, let me use different color. 1 over R square graph will be like this. Sorry, R equal to very 0, it will blow up. R equal to very large, it is going to 0, and kind of this. Okay. Now what were minus 1 over graph? Alpha is positive constant, so minus, so everything will be negative, and for r equal to 0 it will be minus infinity, and for r equal to very large it will also be negative but going to 0 from negative side. So this curve is L square by 2 mu r square. This curve is basically alpha by r curve. So what will be the actual curve then? When u effective will somehow add up these two curve. So if you add up these two curve, then tell me at very close to r equal to 0, what will be the result? Positive infinity or negative infinity?
Negative.
Negative infinity. Who said Shruti? Hello.
Yes, sir.
How it is negative infinity? So we have to see that whether this curve going to infinity, positive infinity faster, or this curve is going to
Oh, sir,
negative
sorry,
infinity.
it's addition. I confused it. It will be
Oh,
positive.
yeah. So this because it will be positive infinity, because 1 over r, this is minus, and plus 1 over r square or whatever alpha and say beta, these are going to 0, this going to plus infinity much faster, because r 0.1, then this will be alpha by 0.1 minus side, and then beta by 0.01, so 10 times faster. Now when 0.001, so it will be minus alpha by 0.001, but beta by 0.00001, 6 not. So okay, 5 not 1. So this will be faster. So your resultant curve will be starting from the plus infinity. So let me draw the with the black or whatever, maybe different color. Okay, and then your this curve, then after certain point it will come to negative, and then at the infinity it will be negative. Now r going to infinity, this will be again this will go to 0 faster. So positive side will be small value and negative side will be less value from r side, right? So it will be negative, at infinity it will be negative. So your effective curve will start from the plus infinity side and go to the minus infinity. So it will be something like that. So this technique you should have to uh, draw curves. So let me now, we know that my u effective curve is like this. R versus. Now I can how I can predict the motion. So the motion depends on the energy. So trajectory will be the trajectory will depend on the energy. So suppose I have E which is greater than 0. So case 1 where I am 53. Okay. Case 1 E greater than 0. Let me write E. So E1, case 1, so E1 greater than 0. So I have energy somewhere, suppose this is my E1. Now can the particle exist this side? This side particle will have kinetic energy negative, because this side potential energy is more. So this side means after this, it will be inside actually, sorry, my drawing is wrong, it will be inside. Oh, sure. Okay, so No, no, it will be outside. It will be outside. Okay. So suppose this is your R1. So particle cannot have position less than R1, because in this side you have more potential energy. This is your U effective. So potential energy more, total energy is constant. So total energy U1 is this much. Then this side for R less than R1, kinetic energy will be negative, which is not permissible, not allowed. Particle can have in this side. So in this situation, case 1, the R should be greater than R1. R1 is this, so it cannot be. So this is particle exists here. Okay, good. This you understand. Now what happened? Particle comes here and comes here and closer to R1. So what will happen at the point R1? So at R equal to R1, your E1 will be U effective, right? So your kinetic energy is 0. That means particle will take a turn here. So particle comes from this side, take a turn, so coming that, and particle will go back. Go back to where? Now if potential kinetic energy becomes 0, kinetic energy becomes 0, so particle will take a turn, cannot move, so it will take a turn, and then it will go where? Go to infinity. No other turning. Suppose I said you are not allowed to take a turn. Now you start from your hostel. Okay, so you start from your hostel, you are allowed to move on a straight line and no turning. Where you will reach? You will reach at infinity, because you are not allowed to take your turn. So you will never return back. So this will be a open path. If your energy greater than 0, then this problem you will have a open path. Particle will come and particle will go to infinity, and that too particle can have only R should be greater than R1, this side. Particle cannot exist, this is not allowed in this situation. Okay, so case 1 is fine. Now case 2. So your E equal to say E2, and that E2, let me draw this curve again. Okay, so suppose my E2 is here, less than, so now E2 is less than 0, and anywhere less than 0 it will cut in 2 places, that is for sure. This is R1, this is R2. If you have very less negative energy, it will cut very far, because it is eventually going to 0. So it will anywhere, so you can have energy, you will cut here. If you have more closer, it will cut to 2 points. So 2 turning points. Now you can understand these 2 turning points. Now can the particle exist at R1? First you see, can the particle exist at R less than R1 or R greater than R2? This is R2. So this region or in this region, can particle exist? So that we have to check. Whether you have to check kinetic energy cannot be negative. So that we have to check. And here is the potential energy is same as the kinetic energy in this point. But now if you particle come in the left, then potential energy is more. So kinetic energy has to be negative. So particle is not allowed. So this is not allowed. So forbidden. Similarly, here, sorry, in this point. So here again, your kinetic energy and potential, your total energy is same as the potential energy. So this is also kinetic energy is 0. Now here potential energy is more, less negative, that means more, less negative means more. So you cannot have here. So particle, this is also not allowed, this is not allowed. But particle can have in between R1 and R2. What will be the motion? The trajectory will be close or so this is suppose your So this is your R1, suppose this is your R2. Okay, so this will be, particle will have this motion in between R1 and R2. It cannot go beyond R1, it cannot cross, but that doesn't mean the motion will be close. Motion will be close, but orbit may not be close. If you have an elliptical orbit, you know the semi major and semi minor axis, if you have R1 and R2, it can have an elliptical orbit. So in this situation, one possibility is the elliptic orbit, but even particle may not have a closed orbit. That I will explain in next class. So today is 12 o'clock, so I will stop here. And there are other cases and other examples also we will consider. So do you have any question? And attendance is very poor. So this will affect your grading, sessional grading. Those who are not attending, and you understand your assignments. I'll check your attendance from your practical class who are in the campus, and all has to submit a hard assignment set in my office. And I am requesting you again that you should not copy each other. In any case, you will copy. I want to find who has copied. I can always find who has copied. But that I'm not I'm asking you not to do that. Okay.
Sir,
Okay,
can you
so
please explain R greater than R2 case?
R greater than R2 case means here. Forget about this upper line, it will confuse you. This line I just for example. Okay, so this, oh no, I'm not old, I'm very old now. This. Okay, so when R greater than R, then R greater than R, maybe I'll explain this. This is more negative, more less negative, so it is positive. So in this point you can have the total energy has to be E2, then your kinetic energy has to be negative, because this is less negative plus some negative will make you the E2. So that is why it is not possible. You think of it and I'll explain later.
Okay, sir, I got to think
Okay,
something.
okay, okay. So